We're going to start with C, that's not a C, Cu2S. We're going to try and find out what's this called, first of all, and what's the charge of each of our atoms and how we can determine that, okay? So if you were just going to tell me the name of just this chemical formula, what would the name be? If you were just going to tell me the name, what would it be? Yeah, Nicole. Copper sulfide. Okay, which is partly true. The name is copper sulfide. But if you look on your periodic table, you'll see we have two versions of copper. Copper plus 1 or copper plus 2. So now we have to determine which version of copper are we using. Which one are we talking about? They behave differently. They interact differently. Right? They have different charges. So we need to make sure we understand which one we're looking at. So the way we can determine this is to kind of work backwards from our chemical formula. A lot of you guys like to use that crisscross method, which works all the time when you're putting together compounds. When you're trying to break them up a little bit, it maybe doesn't work as well because you could have reduced those subscripts, right? So I want you to think about that as we're walking through this. For right now, let's take a look, okay? If I reverse my crisscross method and I bring this 2 up, what number do I know has to be here? A 1, right? If it's a 1, I leave it off. So I'm going to bring this up. Okay, this is for me to find their individual charges so I can determine which version of copper am I using, okay? So if I crisscross these back up, that leaves me with copper plus 1 and sulfide minus 2. Sulfide's charge, right, the anion's charge never changes. So does this -2 match what sulfide's charge should be? Yes. So that means there was no reducing that went on, which means the copper that we were using was the plus 1 version. Okay, does that make sense? If the anion's charge matches what it should be, that means we didn't reduce anything. Okay, nothing was reduced when we put them together. Which means the copper we used was plus 1, which means our full name here is copper 1 sulfide. So this is the actual full name of that. Anytime you use a cation that has a multiple charge situation, you have to include the Roman numeral. You have to include that Roman numeral. Okay, if you leave it off, it's not correct. Okay? Are we ready to try another one? Let's find out what our charge is in this, or what the name of this molecule is. Okay, if you were just going to say the name, right, disregarding the Roman numeral for right now, what would it be? Iron what? Nitride. Okay, iron nitride. But then we have to understand that, oh, iron is one that has multiple charges. So now I need to figure out what Roman numeral has to go here. Okay? So to figure that out, I'm gonna do that reverse crisscross method, okay? Or you can think about the charges that go into that, but let's just look at this reverse method for a second. I cross these back up. How do I know that iron always gets the plus? Yeah, because it goes first, right? And the first one always gets that plus charge. So once I've reversed these charges and I can see here that I'm at a plus 2 and a minus 3, I check my anion. Is minus 3 nitride's normal charge? Yes, which means there was no reducing that happened when I put them together, right? Which means what version of iron am I dealing with?
2.
Plus 2. So I put a 2 Roman numeral in parentheses. Okay? Questions so far? Doing okay? Okay, so far we've looked at ones that have not been any reduction. Nothing has happened in terms of reducing these down, right? If I wanted a compound between iron 2 and nitride, that's exactly what it looked like. I would start with Fe plus 2 and minus 3, and I would crisscross them down to form my compound, and it would look just like this, right? That's exactly what we started with here. So we're just reversing that crisscross method. Now let's take a look at a very similar compound, Fe N. Right? If you were going to name this compound, disregarding the Roman numeral at this point, what would it also be called?
Iron nitride.
Iron nitride. Okay, so iron nitride again, but there's something that's different. Right? The ratio of iron to nitride atoms is not the same, which means something has to be different with iron. Okay? So now if we do our reverse crisscross method, we have a 1 and a 1 right here, right? So if I reverse these up and I say that iron is +1 and nitride is -1, is that the real charges of these?
No.
Is that the real charge of nitride? That's what I should be asking. No, what do we know nitride's charge has to be?
3-.
So if nitride has to be 3- and we see over here that we have a 1-to-1 ratio, what does iron's charge have to be? +3, so which means what goes in my parentheses here? Iron 3 nitride. Okay, does that make sense? When you see that reduction happening, you've got to check the anion for its original charge. Okay, if you don't use the crisscross method, then you're just looking at charges itself, and you should understand, or you would be able to see like, oh, these are a 1-to-1 ratio. I know nitride is always -3, which means iron has to be +3. Okay, if you're just looking at the charges themselves and you don't use that crisscross method, which is fine, you're going to have to identify it just based on the charges. So this is our final answer. If you give me iron nitride with no Roman numeral, that's no good. Right? Because we can see that the difference between iron 2 nitride and iron 3 nitride is a whole different ratio of atoms. Okay? Questions with that? Okay, let's try a couple extras here. I'm going to try now to give you the name, and you're going to write the formula. Lead 3 sulfide. I should also point out right here I'm using lead 3. You see on your ions, lead 3 is not even an option, right? These are your most common ions. They can have other ones too, so you just trust what the Roman numeral tells you. Okay, these are your most common ions, but lead 3 also exists, it's just not as common. So you trust what your Roman numeral tells you. That even though we don't see Pb +3 on here, right? Lead is Pb, are we finding that? It's way down here. 82. Okay, even though 3 is not an option on there, you're still going to trust what the Roman numeral is telling you and make 3 its charge. Okay, Aiden, what do you think?
I got
PB2S3. Raise your hand if you agree. Perfect. Good. Lead is a +3. Sulfide is a -2. Very good. Any questions with that? So Roman numerals are important. They always tell us the positive charge that goes with that cation. Okay, always tells us the positive charge. Okay, let's try a couple more. I'm going to give you the formula now. Okay, so I have 2 different compounds up there. I want you to give me the full name of both of those compounds. So as we start naming with polyatomic ions, Most of our polyatomic ions have a negative charge, all except ammonium and ammonia. Right? Did I give you both ammonium and ammonia? NH3 and NH4 plus 1? I don't really remember, but all the rest of them have negative charges, which means they're going to come first or second in our formula. Second. They're going to come second, okay? Polyatomic ions always get to keep their name, so it'll be called phosphate and phosphite and whatever. There's no IDE that gets added to the end of that, okay? So I want you to kind of look through this sequence. N with a -3 charge is called what? Nitride. Nitride. Okay, so an IDE means it's an element by itself. NO2 minus 1 is called nitrite. NO3 minus 1 is called, you don't necessarily have to write this down, sorry. It's called nitrate. Okay? There's kind of a sequence here. I want you to understand that the ATE ending does not always mean 3 oxygens. That is not the case. There is a rule you can remember, though, and I pointed this out last time just briefly. Between ate and ite, what's the only thing we see a difference? One less oxygen. Between ate and ite, the only difference is that there is one less oxygen. The charge does not change, okay? So if you look between nitrate and nitrite, the only thing that's different is one less oxygen. The same rule is true for phosphate and phosphite. PO3 minus 3 is phosphite, and PO4 minus 3 is phosphate. Okay, so like I said, 8 does not always mean 3 oxygens, but ite always means one less oxygen. So as you're memorizing, if you can remember the 8s, then you automatically know what the ite version is. Right? If you can remember what phosphate is, you can know what phosphite. Right? If you remember that rule. Okay? But I want you to understand the difference. IDE means just the element by itself. If we see an 8 or an ite, that means we've got an oxygen tagged onto it, and that becomes our polyatomic ion. Right? That's now a version of our polyatomic ion. So, let's start naming with polyatomic ions. If I have this formula, LiNO3, the polyatomic ion gets grouped as a whole, okay? And it does not need parentheses until you have more than one of them, and we'll talk about that here in a second. But lithium has what charge? +1. Nitrate as a whole has a -1 charge, so they should come together in a 1-to-1 ratio, which means our final answer is LiNO3, and the name of that compound is lithium nitrate. Lithium nitrate. Okay, so naming with polyatomic ions is very simple. It's just really everything we've been doing, except now we're using our polyatomic ions instead of just regular anions. Okay? So if I give you this formula, or this name, calcium sulfate, okay, can you come up with that chemical formula? All right, so if you're kind of stuck, that's okay. Calcium is a +2. Sulfate is SO4 -2. So what's the ratio need to be when these combine? 1-to-1, right? So our final answer can be CaSO4. Right? If there's both 2's, right, if you have a 2 and a 2, they reduce, okay? And so we get rid of those. So CaSO4 is our final answer there. Uh-huh.
So what happens if, like, wait, I'm just trying to make sure I understand.
Yeah.
So the charges, since they're, like, opposite, like, they canceled out. Right?
Mm-hmm.
Okay. And
Yep.
they just left.
So then it's a 1-to-1 ratio. So we could have put a 2 and a 2, right? But then once we're here, these reduce.
Oh.
So then they come back to a 1 and a 1. Something that you need to understand is if I have a 2 here and a 4 here, those are not reducible. The 4 is part of the polyatomic ion. So once you have a polyatomic ion, you never alter the subscripts of a polyatomic ion. Okay? So you never change anything that's, the anion itself, the polyatomic ion. That is not reducible. Okay, but I will show you, let's practice some now that we could do that with. We could reduce with. Let's say I want magnesium nitrite. Magnesium nitrite. Magnesium's overall charge is +2. Nitrite is a -1, and I wrote down nitrate, sorry, NO2. So if I'm looking at these charges, how many nitrites do I need to balance out magnesium? 2. And if I use my crisscross method, I would see the same thing. So I would be left with Mg1 NO2 2. So here's the problem, right? We can't just have two subscripts hanging out right next to each other. Anytime you have more than one of a polyatomic ion, you put it in parentheses. So you use parentheses anytime there are more than one. So I would write that down. Use parentheses if you need more than one of a polyatomic ion. Okay, and Pi just means polyatomic ion. Uh-huh.
So is it okay if we leave the 1? Or
Yeah, you can get rid of the 1. Sorry, I just hadn't got to that yet. Yeah. Get rid of that 1. So your final answer would be MgNO2 2. So this is telling us right here that we need 2 of this whole molecule, which means we would have 2 nitrogen atoms, and how many oxygen atoms would we have? 4, right? If we need 2 of this whole molecule, we would have 2 nitrogen atoms and 4 oxygen atoms. Okay? Any questions? All right, let's try a couple more here. I am going to ask you to write the full name of that molecule. And then I want the formula of the next one. So these are 2 different compounds. They both just happen to use iron. Okay, I want the name of the first one and the formula of the second. Iron phosphate. Are we missing anything?
Yeah.
Iron, what'd you say? Roman numeral 3. Good. You have to say that. So the way you would say it when you just speak it is iron 3 phosphate. Right? You just say iron 3 phosphate. So did everyone have that with the Roman numeral 3 and everything? Good. Okay, a 1-to-1 ratio here means I know phosphate is always -3, which means in order to have a 1-to-1 ratio, iron has to be +3 also. Okay, next one, iron 3 hydroxide. Let me find someone that hasn't talked yet. All right, Nick, go for it. FeOH2, like this. FeOH2, like that. Okay, anyone have anything different? Okay, Johnny, what'd you have?
I had FeOH3.
OH3, like this?
Yes.
Okay, anyone have anything different? We're getting closer. Nicole, what do you think? Bingo. Here's the problem. We needed more than one hydroxide atom, didn't we? Okay, so let's work from the beginning. Iron, we said, was +3. Fe +3. That's what the Roman numeral tells us. Then we know hydroxide is -1. If I cross these down, that tells me I need 3 of my whole molecule. If I leave it like this, that means I only need 3 hydrogens. Okay? If I put my parentheses, then that's telling me I need 3 of my hydroxides. So there's a difference there. So you have to have that parentheses if you have more than one of our polyatomic ion, which we needed there. So Fe parentheses OH parentheses 3. Very good. Okay, how many of you had exactly that with the parentheses and everything? Great job, Nicole. That's tough, okay? The parentheses seems like it's not a big deal, but it is when you say it the other way. So if I say just without the parentheses, that means I only need 3 hydrogens. You automatically all went, oh yeah, right? You knew that was not the case. We didn't just need 3 hydrogens. We needed 3 of our whole molecule, which is why we include that parentheses. Okay, do you want to do a couple more? Okay. Let's try this one. Chromium 2 bromide. CrBr2. Agreed?
Mm-hmm.
Yeah, good. Chromium was a +2, which is what our Roman numeral tells us. Bromide was just Br minus 1. All right, very good. Alexia, what did you have on the second one? Okay, that's okay. Let me find someone that hasn't given us one yet. Jack, what do you think?
Silver carbonate, but it's silver 3?
Silver carbonate. Nope, you can just stop with silver. So, if it does not include a multiple charge situation, which silver doesn't, right? Silver doesn't have multiple charges. You don't include the Roman numeral. Okay? So if we reversed our charges back up, right? Carbonate is a +2. Down here is really a 1, right? The 3 is not part of the charge. It's the 1, right? The 3 goes with carbonate. So there is a 1 outside of those invisible parentheses, right? So that's why it's just silver +1. And if you think about it in terms of the charges, right, we know carbonate is -2, and I needed 2 silvers to cancel that out, so each of those must be +1. Okay, does that make sense? The 3 itself is part of carbonate. That's why it's so important for you to know the polyatomic ion, to know carbonate is CO3 -2, right? So the 3 doesn't become part of that crisscross method. So just silver carbonate. You only include the Roman numerals if it's a multiple charge situation. Okay, not for ones that only have one option. Okay? Questions with that? Okay.